YouTube that I can stop recording them. He's got very radical views. He thinks benzenes have 6 sides. Get him, right? So anyway, and so basically what we had thought about so far, what we had discussed was the idea that once we have an aromatic system, there has to be a unique set of chemistry that's done to be able to react with it, right? But what we also saw is that, not all aromatic systems behave in the same way. So we went through those examples of anthracene and phenanthrene last time there. And we saw that, certain of the pi bonds are going to behave in, let's say, the more expected manners that we've seen before, right? So they essentially end up behaving just like a generic alkene, right? Or in some cases they end up behaving like a conjugated 1,4 system or something like that, right? But the point is, when we go through our mechanisms and we can rearrange to make aromatic rings, then that's going to be a strong driving force of the mechanism itself, right? So the point being, right? The point being that if, I don't know, my computer's still acting dumb too. I still haven't figured out what's going on with that. But anyway, life is life. So, but anyway, if we go through and we tried this, right? There's just not enough oomph in there. There's not enough reason. There's not the right incentive to get this to do anything, right? So we're not going to see any reaction in this case, right? So we have to do something else with it, and that's what we're going to talk about today, right? So what I'm going to do is show you guys the mechanism. All right, here it is, right? So here's all the mechanism for the rest of the for the next, chapter and a half. Got it? Okay. What we do is we generate an E plus. Okay. Good. No questions. Excellent. Moving on. Okay. That's gonna attack the E plus. Okay. When we attack the E plus, this gets made. Good. And then the B minus comes in. Okay. We'll notice that the B minus grabs the hydrogen where the E was added. Got it? And we do an elimination, and remember, whenever we do an elimination, we end up making a pi bond, and we end up regenerating our aromatic ring. Okay? Okay, questions? Nothing? All right. So what we're going to do in the... So that's it. That's the mechanism. All right? That's the mechanism. So real quick. Right? Real quick. What is going on here? Right? So what is going on here? Let's see. I don't know. Right? It looks very odd. Does it? Is there anything really different here than what we've seen before? A pi bond and swinging out and grabbing something with a positive charge, right? The pi bonds having, or acting as a negative to grab something positive. Have we seen that before? Yeah, right? So this is just electrophilic substitution, right? Electrophilic substitution. We're adding an electrophile. What's an electrophile? Something with a positive charge, right? It files some electrons, right? Got it? That's all this is. Electrophilic aromatic substitution, EAS. Okay? EAS. We're going to learn nucleophilic aromatic substitution, NAS, a little bit later. But EAS is where we spend most of our time. Okay? So what is the E plus? It's an electrophile. Got it? Have we dealt with electrophiles before? Yes. Okay, yes. Right? Yeah, we dealt with them quite a bit, right? So the difference, all the mechanisms are going to work the same way. Got it? We have to generate that electrophile. It gets added to the ring. and then we reform the ring. Got it? That's all that's happening here. Generate the electrophile, add it to the ring, and then reform the ring. Now take a note, I'm going to tell you where you guys are going to start to miss points already on the exam. Ready? It's going to be which hydrogen gets eliminated. Alright? You guys are going to pull off the wrong hydrogen. It's the most missed thing. Okay? Which hydrogen gets eliminated? The one where the electrophile got added to. Got it? Is that going to be different? No. Okay. Always going to be like that. So where do things change then? Well, where things change is how we generate the electrophile. Okay, that's it. That's the only part that changes. Everything else, boring, easy, just like all the rest of organic chemistry, right? No problem. Very predictable. 30 minutes of studying for an exam, that kind of thing, right? Good? You guys aren't disagreeing and you started worrying me. All right. Go, Dr. H. Every day, 5 hours. Okay, good. All right. So, first, the classic. No, we won't do the classic first. Let's do something else. Then we'll do the classic. It'll be great. Fun. You guys will remember it for the rest of your lives. So much like the first reaction that we learned back in the easy days of Gen Chem 1, right? We learned how to add something to a pi bond. Guess what we're going to learn here? Pretty much the exact same thing, right? So we have to add a halogen, because we know how useful all of our halogens are. Okay, so we got this. Very good. We want to add a halogen. Fantastic. We're going to add some chlorine there. Okay. Chlorine's nice, cheap, right? Get a bottle of chlorine, keep it in your car, you never know when you need it, right? That kind of thing. Right? I'm sorry, I'm just all over the place this week. Right? And then we need to add something into there. We need to add some AlCl3. Now, what in the world is AlCl3? Well, AlCl3 is one of these extremely common industrial chemicals. Okay? Aluminum is a powerful Lewis acid, right? And Lewis acids are great, because guess how Lewis acids behave? Like an acid. Got it? Okay. So why don't we just use a regular acid, like a sulfuric acid? Well, first of all, there's no such thing as a regular acid, right? We've just been calling acids, we've just been calling Bronsted acids, right? It's just kind of the ones that we deal with most commonly, right? But Lewis acid is what? What's the definition of a Lewis acid? The definition that deals with protons is a Bronsted definition, right? So Bronsted acids and bases are all with protons. Lewis acids and bases deal with electrons. Oh, you guys got a 50-50, right? I heard both answers so far. But you say it real quiet so that it's not recorded. Because otherwise, people are going to comment and say, who's that girl with the brown hair? And said it's a donor. And there's going to be like thumbs up on that. And try to track it down. Her head goes down, just turn a little bit red. That's okay. No, right? So you got an option, right? We're either accepting electrons or we're donating electrons, right? So what's a Lewis acid? It accepts. How do you know? Because it's an acid, and acid begins with A, right? So it has to accept, right? Yeah, that's how I remember it, right? Okay? But you guys already knew that anyway. Dr. H, I don't want to remember things the easy way. I want you to overcomplicate it and explain it to me in a way that I won't remember and then say, yeah, acids, acceptors, that sounds good, okay? So what is AlCl3, right? There it is. Got it? Carbon pairs. Nice, easy, Lewis structure. Awesome, fantastic. Behold. What's odd about this? Aha! Aluminum does not have an octet, and yet it still does not have a formal charge, right? It looks like we might be deficient of that octet in terms of available electrons to the aluminum, right? So we might expect it to have a positive charge, and yet it doesn't. Okay. What else do we notice? I forgot the Jolly Ranchers again. So I was talking to my morning Gen Chem class, right? Sophia, this is important. I don't care what you have to say. I got to talk. I was talking to my morning Gen Chem class. I was asking, talking about the exam and this kind of thing. Do we have any questions? One young lady in the back. I know her known associate. Dr. H, how come we don't get Jolly Ranchers? So, that's okay. I got 5 pounds of them to get rid of, but I just forget them, and then I need to bring them for you. So I forgot about that. I'm sorry. So I'm sorry, Sophia. What were you saying? I need to tell you guys about my day-to-day life. What's up?
Would the chlorines be doing kind of like the inductive effects and
What do you mean?
There would be electron withdrawing?
Aha, right? So we have 3 fairly electronegative atoms bound to a central metalloid, right? Aluminum, right? We can probably call it a metal. That should be fine, right? So not all that electronegative of an atom surrounded by pretty electronegative halogens, right? So what does that mean about the aluminum?
It's feeling partially positive.
It's feeling partially positive. That's important, right? What else do you guys notice about it? It is planar, which means what?
Things can be added on top of bottom.
Aha, that's very important, right? So it's planar. That means in terms of how we add things, right? We can add from either face. What else does it mean for it to be planar? Yeah.
Electrons won't bump into each other in a sense, how when we're doing range structuring in OChem 1, how, depending on where the electrons were, it would sometimes interact with each other. Never mind, I don't even know what I'm saying.
Now I'm trying to figure out what we would. I'm not sure what you're trying to get at with that.
Axial and the other thing, and how.
Yes, I've heard of those.
how depending, the bigger molecules with the more
So what's Taylor trying to say?
Sure,
Sterics, right? Right. So she's trying to talk about sterics. Now, that's not really going to have an impact here, right? Sterics is always something to consider, but with a planar molecule, right, we got kind of basically 2 open faces. We're going to have a steric issue here. So if it's not sterics, then it's electronics, right? We talked a little about the partial positive charge due to induction. What else do we know about electronics, aka where electrons can live if we have a planar compound? Huh? What?
Hamburger buns.
Hamburger buns. I don't know what you're trying to get at with that. What do you mean by that?
That there's no pi bonds here, so then it's stupid to be saying here, but how they can all share one
Molecular orbital.
that.
Yeah. you're on the right track. But we can step away from molecular orbitals here.
It's just an empty orbital.
Aha, what has an empty orbital? Why? Only has 3 bonds, so what's its hybridization? 2, which means it has an unhybridized p orbital, right? And that unhybridized p orbital is pointing above and below the plane of the aluminum, right? 90 degrees from the rest of the atoms. Easily accessible vacant p orbital on a positive feeling metal, right? You guys get what I'm saying with this? You guys catching what I'm throwing down, huh?
Are you picking up what you're putting down?
Huh?
Are you picking up what I'm putting down?
Is that what it is? I don't know, I'm from North Carolina, I just make crap up, right? Alright, so, we got that. You guys catch what I mean with this? Okay, so tell me what's the first thing that happens in this mechanism. I told you that this is an acid. Where do we use acids? In the first step. So where are you going to use a Lewis acid? How is that different from everything else we've learned? It's not. You guys catch why organic chemistry is easy? It's all the same, right? Man, this is boring. Why the hell would anyone want to do this for a living? Jeez. Man, you guys biochemists? Find something else. All right. All right? But it's going to work the same way. If it's an acid, we can probably make a safe assumption that's going to be used in the first step. So if it's a Lewis acid, it's going to act like a Lewis acid. It's got a vacant p orbital that's feeling positive. So what's it on the hunt for? Electrons. From what?
Pi bond.
I didn't say this was an electrophile necessarily, right? Pi bonds aren't all that reactive, and look what has to get added to the benzene. What are we adding to the benzene ring?
Cl.
Cl. So what's our electrophile?
Cl.
A Cl.
2.
So in the original mechanism, right? Think about this, right? In Mr. Generic mechanism,
It's a base.
what is that? E with a? Aha. So what's going to be our electrophile in our mechanism? A Cl with a, weird, isn't it? Have we ever seen that before? No, right? So we have to generate a chlorine with that's feeling pretty darn positive. Or if we want to think about this a different way, we want to weaken that chlorine-chlorine bond in some way. So what's going to happen first? Well, we got our good old buddy chlorine, right? What's more reactive, some lone pairs on a chlorine or a pi bond? Probably our chlorine lone pairs there, right? I'm generalizing things a lot, right? Of course there's, I always make the joke like someone online's going to leave comments about this, but they're not, but I don't want to. Well, look, when I'm dead and gone in 50 years, these are going to blow up. They're like, man, we lost a good educator. Right? Why are you guys laughing? Oh, man, geez, my feelings. Do what? What? Go ahead, I just speak up.
I love how you're giving yourself a years though.
Alright. Right? So what do we have here? Right? Lone pairs from the chlorine are donated into that vacant p orbital, right? What did we do?
Made another bond.
We made a bond. What else did we do? All actions have consequences, right?
It's not planar anymore.
It's not planar anymore. What else did we do? You're gonna keep chasing that horse there, huh? eventually we're gonna catch it. What's up?
The chlorine's gonna have a positive charge.
Aha, right? So because we ended up taking one of those lone pairs of the chlorine and making a bond with it formally, right? Formally it has a positive charge. Now, does that chlorine really have a positive charge? No, right? What else formally has a charge now? Well, there's got to be a balance in life, right? If you generate a positive, there's got to be a negative somewhere along the way, right? Something's got to be there to balance it all out, right? Sometimes it's sodium and you can ignore it, that kind of thing, blah, 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 right? But in this case, the negative is on the chlorine there. Is that chlorine really feeling negative? No. Excuse me, yep. I said that backwards. I meant to say, is that aluminum really feeling negative? No. Right? Is that chlorine really feeling positive? No. What are these formal charges telling us? Hey, pay attention, there's something odd going on, right? But, much like when we have an oxygen with a positive charge, how do we help that oxygen with a positive charge? You can't just give things electrons. Okay. I got an oxygen with a positive charge. That's the best way to get rid of that positive charge. Remove a hydrogen, right? Get rid of one of the things it's bound to. Weaken the bonds to one of the things. Got it? So what does this tell me that we have a chlorine with a positive charge there? We're weakening the bonds to that other chlorine. Okay? So which chlorine's actually going to be more reactive? Well, it's going to be the one on the outside there. Okay? You guys with me on this? Sometimes what they do is they, Sure. Sometimes what happens is you'll see this drawn as Cl plus, right? Sometimes you'll see it drawn like that, right? Wherein this bond here, they kind of just go ahead and break that. You're not technically wrong with that, but you know, I don't know what the concentration of Cl plus in a solution like this would be, to be honest. I'm skeptical. What's up?
I understand why the chlorine, like the furthest chlorine, is the most reactive, but like why? Like what are, like, can you put into reasoning?
Why is that one going to be in?
Yeah, rather than the one with a positive charge in a sense.
Give me a one-word answer, do you think?
I was gonna say something funny, so I'm not.
I'm setting you up for this one. You've been there you go, right? So that's one reason, right? You've got to kind of weave your way in to get to that one chlorine there, right? And it's bound to a metal, right? So that's going to make a pretty strong bond. You'd have to break that chlorine aluminum bond, right? And then, you know, go on and do something else with it after that, right? So the chlorine-chlorine bond is going to be weaker than the chlorine-aluminum bond also, right? So if you looked at the dissociation energy of those two bonds right there, chlorine-chlorine is going to be weaker is what it is, right? That's why chlorine is so reactive to begin with, right? Cool. So both of those are technically right, but you know, one I would say is a little bit more correct than the other. Right? Okay, cool. So what are we going to do here then? So now that we know how to generate the electrophile, right? So let me put a green bracket around everything here, right? So this is generating electrophile. Generating E plus. All right. Now what happens? This, right? Got it? So we've taken care of that part of it, right? We made the E plus. Now you just go through and do everything else, right? So let's see if we can put that all together here then. Here's this. I think I'll leave the lone pairs off at this point. I think you guys got it. Right? Swing out, grab that chlorine, make a bond, break a bond, right? we've got this, and we've got that, right? See, does the book, real quick, let me check something here. They talk about this stuff, and I'm pretty sure they talk about sigma complexes. Let me just double check. Oh, well, whatever. Oh, there it is. Well, they really don't. That's kind of weird. Oh, they do. Okay, sorry. Yeah. So this right here, when you see the book talk about sigma complexes, right? Now, the reason why they talk about this is because, again, if we were going a little bit more in depth with all this stuff, we'd spend some more time dealing with the sigma complexes there, right? And just the who, what, when, and why, that kind of thing. Now, what do I expect you guys to know about it, though? Well, what do we have? Ignoring everything we learned recently about aromaticity and all that. What do we have? That's a carbocation. And what's it next door to? True. That is true. It's also next door to a. Heard somebody say. So next door to a pi bond. In fact, it's right next door to it, which makes it an allylic position, which means what? It has resonance, and we can delocalize that positive charge around all those pi bonds there, right? Good? Now that's going to be important. Okay, we're going to get back to this idea of delocalization of positive charges, blah, 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 blah. Okay? It's going to be really important. And they talk about that in the book, and they, sigma complexes, blah, blah, blah. What does it all come down to? It's a carbocation. We have to worry about stabilizing. That's it. Got it. Right? Do we have to treat this any differently than what we've treated carbocations before? Nope. Right? That's it. We just have to make sure that we draw the resonance structures, and we can draw the resonance structures, and after we draw them, what do we have to do? Look, right? And after we look, we go. Got it? That's what it is. That's it. Like seriously, I could just stop here and we could go watch Terminator or something, right? That's right, and then that's the rest of these 2 chapters that we have. It's all going to look like this. Make some kind of positive charge, okay, delocalize it, check to see where the most positive is that good or not, then go on with life. Right? That's really all it comes down to. Okay? Now, here's where the most common mistake happens, right? Now we have to reform our aromatic ring. We take the hydrogen where the electrophile was added. Okay? I'm going to draw you guys 2 sets of arrows here. I know which one you guys are going to use, but I'm just going to show you guys both ways. Now here's, oops, put that, sorry, I forgot to put that negative charge in there, right? So now we have this. Now something with a minus charge has to come in and grab that hydrogen and reform our aromatic ring. Now something I didn't tell you guys earlier, but AlCl3 is catalytic, which means what? It's reformed at the end of the reaction. Got it? So right now, do we have AlCl3? No, we have AlCl4. Okay? So we have to regen AlCl3 along the way, which means one of these chlorines has to pop off and we get our starting material back, right? Our starting catalyst. So here's what happens. Right? Okay. So the aluminum chlorine bond, right? This gets made, that gets made there, right? So those 3 arrows right there, okay? That's what's happening on a step-by-step basis. Got it? So to make things a little bit easier, to make things a little bit more streamlined, right? Black looks good. This is what you often see right? So instead of we start my arrow at the aluminum chlorine bond and send those lone pairs to go grab the hydrogen. Got it? Is it any different than the orange arrows that we had up there? No, right? At the end of the day, we break the aluminum chlorine bond and we make the chlorine hydrogen bond. Got it? Whether you want to do the 3 steps or the 2 steps. I always prefer to do the 3 steps just because it's easier for me to kind of visualize what's going on with it, but it doesn't make a difference. Thank you. Okay? It doesn't make a difference. Got it? So whether you want to show it like this, or like that. Okay? Good? And what do we have at the end of this? Plus AlCl3 plus HCl. Right? We bubble off some HCl along the way, life is good. Okay? Very, 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 very common reaction. Okay? Very easy reaction to do also. Works great. No real problems with it. Easy to work up, usually. Good? I'm going to change things up drastically. You guys ready? Thanks. Good. Okay, show me the mechanism. Oh. looks like everyone's got the mechanism. How's this different? It's not, right? What happens first? You have to generate the electrophile. The bromine attacks the iron, right? Fe. We weaken the bromine-bromine bonds, right? Pi bond comes in, attacks the outside bromine, goes through, does the rest of the work there, right? Cool. So now we can add an aluminum. Now we can add a bromine. Excuse me, now we can add a chlorine, we can add a bromine. Iodine's a little bit different, as it tends to be. There's always like something kind of funky going on with iodine. But in general, it works the same way. So I2 with some nitric acid, not nitrous acid. That'll do the trick. Or apparently you can use I2 with some mercury oxide. Or use CO2. Or some copper 2 oxide. Okay, fantastic. So all these things end up at the same place. Now, iodine's a different beast. Okay? Iodine kind of is known for kind of dissociating and making some of these different aggregates in solution. Basically, it's not too hard to generate I+, okay, as compared to Cl+ versus Br+. So all we're really doing is adding some stuff in there that kind of just shifts an equilibrium around, right, and just generates I+ a little bit more in solution is all it is. Okay? So mechanism's different, especially when we're getting to the stuff like the copper oxide and mercury oxide there. So don't need you guys to know those mechanisms. In fact, I don't even think they're in the book anywhere, right? I don't even know if I could bust them out off the top of my head, but that's something for inorganic chemistry, right? Which we don't teach here, so guess what? You guys will never know these mysteries of life, right? So anyway, but we can add all 3 of the, I don't know, do we want to say normal halogens? The ones that we see most commonly. We will later on learn how to add fluorine. Now, we tend to ignore fluorine a bit in this class, just because, just like iodine is a different beast, like fluorine's a completely different beast too. Right? The chlorine and the bromines are mostly predictable, kind of easy enough to handle, but fluorine and iodine kind of live in their own little world most of the time. But fluorine chemistry is extremely important, especially in the pharmaceutical industry. Right? Adding fluorine groups and swapping it in for hydrogens and things like that is extremely important. And so we'll learn a way how to do that later, but we have to learn a different mechanism before we kind of get there first, is what it is. Right? So at the moment, fluorine's kind of out of the picture. Right? But we can make all these different halogenated benzene rings. Right? Cool. We demand more. Give us more. All right. Go on to the next most common thing. Nitration. Nitration is going to be extremely important also. But again, it's not going to be immediately evident why. Now, we haven't talked too much about nitro groups, okay? But as soon as you kind of get to the aromatic chapter, nitros start to pop up everywhere. All right. So, we take a benzene ring, and we dump in nitric acid and sulfuric acid. Now, what do we know about nitric acid and sulfuric acid? They're very, very powerful acids, right? Both of them fall into the strong acid category, right? We've seen sulfuric acid everywhere, and now we see it yet again in another place, right? And now we've got nitric acid in there. And yet somehow we have... Okay. And yet somehow we have to add an NO2 group. What's the electrophile that we're going to generate then? NO2 with a positive charge. Got it? All right, so here's the electrophile I have to generate. Weird. Okay. See what you guys come up with. I'm going to ask you guys a question that you know the answer to. How do acids behave? Like acids. Got it? What's a stronger acid? Sulfuric acid is. So how is sulfuric acid going to act? Like an acid. Got it? So see what you guys can come up with. You got 5 bonds of the nitrogen, right? Much fluid structure. Start by drawing out fluid structures for nitric and sulfuric acid. Draw the right fluid structure. Good. Where's your positive and negative charges? How does all of chemistry work? Something negative, find something positive. But to know where the negatives and the positives are, we have to draw the Lewis structures. But be careful what the formal charges tell us. But there's something unusual going on, right? Nitric acid and sulfuric acid are ours oxy acids, right? Which means there's an OH group somewhere in there, right? Good? What do we have here? Water is a, so let's make it leave. Okay. So we end up generating that there, right? You guys with me? Anything unusual about this? Yeah, right? An acid acting with another acid, that's kind of unusual. But how do acids behave? Like acids. What's the pKa of sulfuric acid? Look it up real quick. Somebody check it. Somebody look sulfuric acid and somebody look nitric acid, the pKa's.
PK sulfuric acid.
-2.8.
This is -2.
This is -2.8. This is -2. Okay. Thought they'd be lower than that. All right, maybe I was thinking of the wrong numbers. Are you sure about those?
Sulfuric acid's -3 and nitric acid's -1.5.
Now we're getting numbers all over the place. This is weird. Well, maybe I'm just thinking of different numbers. It's okay. Yeah, okay, fair enough, whatever. All right, so -3 for one of them and -2 for the other, right? So what does that tell you guys? So for argument's sake, right, and just to make the math easier, let's say that it's this. So one's -3 and one's -2. What does that mean?
Sulfuric acid is more acidic.
How much more acidic? 10 times more acidic, right? Remember, this is a logarithmic scale, right? So it's 10 times more acidic than nitric acid is. Got it? So if it's 10 times more acidic, how's it going to act? Like an acid, right? Now remember, this is, you guys went through Gen Chem and you know about equilibriums and all that kind of stuff, blah, 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 right? But when you mix those two together, you'll end up making NO2 plus, okay? Which is a good electrophile. And then what's going to happen? Pi bond's going to reach out, grab the. Pi bond's going to hit what? The. Nitrogen, right? So the nitrogen's got the positive charge here, both with the formal charge and how it's feeling, right? It's attached to 2 oxygens there, right? Positive feeling nitrogen. So pi bond reaches out, hits the nitrogen, and then we regen our aromatic ring, right? Good? Anything unusual going on here? No, right? Not really. Here's this. And some kind of base comes in. Might be the water, more, it could be the conjugate hydrogen sulfide there, or hydrogen sulfate. Not hydrogen sulfide. So this might be our base there. Good? What do you notice about those nitro groups on the ring?
Still charges on
Yeah. It's going to be important, okay? It's important to recognize that the nitrogen that's bound to the ring, directly bound to the aromatic ring, has a positive charge on it. That's going to be extremely important. Okay? Other than that, is there anything unusual about this mechanism? No. Okay. All good. Now we get to sulfonation, and sulfonation is going to have an important use for us in a little bit, which we'll probably get into on Friday. Okay. Okay. Now what's going on here? So we got to do a little bit of thinking before we can kind of get to the mechanism. So this right here is known as fuming sulfuric acid. Right? Now the way they make sulfuric acid is they essentially burn sulfur, right, to make sulfur trioxide, SO3, which is a gas. And then they bubble that gas through water. If you have SO3, right, so follow with me for a second. If you have SO3 and you add H2O, what do you make? H2SO4. Got it? So they just bubble that sulfur trioxide through water and make sulfuric acid that way. Now, there's a limit, right? There's a limit to the solubility, right? And so when you just buy good old regular sulfuric acid, it comes at, I think, 16 molar or something like that, right? Really darn concentrated, right? Not to be confused with 6 mole or something, right? But that's all it is, right? They just bubble the SO3 and they make H2SO4, right? But then if they, much like, you can think of it almost like with making a soda, right? But a soda that would instantly kill you, right? If you keep forcing SO3 into solution, right, under pressure, you're going to dissolve some of the SO3 into the solution, right? And so as soon as you open the bottle then, right, you know, you guys see the CO2 bubbles come out, right? Because you're changing the pressure of the system. So it'll start fuming SO3 out. Got it? So that's all it is. It's like concentrated but a little bit more, right? So if you don't think about it like that. So you have SO3 dissolved into H2SO4. Got it? That's all it is. But there's an equilibrium here, right? So SO3 in water makes H2SO4. So how in the world can we add that to our aromatic ring? Well, as with most things in life, the first thing to do would be to draw the Lewis structure, right? So when you're sitting down and thinking about should you invest in GameStop, right? Sit down and draw a Lewis structure and say, maybe, right? No, right? But sit there and draw the Lewis structure of this, okay? So what does SO3 look like? Come on, stupid thing. All right. Wow, thanks, Dr. Ace. That was really helpful. I can see clearly now what I need to do, right? But what's going on? What do we need to do? We need to generate an electrophile, right? We need to generate something with a positive charge. Well, what's really happening here? Well, remember there's a couple of different resonance structures that we have going on, right? So at any given point in time, there's a portion that looks like this, right? We could start to draw all of our resonance structures. Right, got that? Yes? Yada, 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 yada. And we could go back to here, right? You guys with me on this? Straightforward, right? Just simple, nice resonance structures. So do we have an atom that's got a positive charge on there? Yeah, right? So this is happening while it's in solution, and so this is our electrophile that gets added to the ring itself. Okay? So the ring, the pi bonds will end up hitting one of these while it is in solution. So just for simplicity's sake, we'll pick this one here, right? Right? We got this. Something's going to come in and grab that, right? Some base. Right? Is that what we said was going to get produced? No, we said what's going to get produced? An OH, right? So what are we under? Heavily acidic conditions. Right, so that O minus is going to pick up a hydrogen from one of the sulfuric acids very, very, very quickly. Got it? This is a very useful reaction. This is how they tend to make, I think it is, I'd have to go back and double check to see if it's still the truth in modern times. But modern soaps, right? The soaps that you guys made in lab are from carboxylic acids, right? You guys saponified esters and you made carboxylates, okay? Now carboxylates are fine, they're great soaps, they're surfactants, fantastic. They've got a problem that they form soap scum, right? And when you have calcium or magnesium dissolved into water, you make the calcium and magnesium carboxylate salts, which are very insoluble. They're very insoluble, and so then they form that white soap scum type stuff. So more modern soaps are actually based off of sulfates, right? They're based off of sulfates, right? So if you take a look at your shampoo bottles, which you guys will slowly be able to read a little bit more of, right? You see ammonium laureth sulfate, and you see ammonium lauryl sulfate, right? And these are just these sulfate-containing alkyl chains instead, right? Because the magnesium and the calcium salts of the sulfates are slightly more soluble than the carboxylates are, right? And so they don't form the soap scums there. But making sulfates is very important, okay? Now, it's going to have a secondary important reason for us, important reason, that's not what I want to say. And it's going to have a secondary important function for us, is what I meant to say, right? And we'll come back and we'll talk about why that is, right? But for the moment, what do we notice about the mechanism? It's exactly the same. You guys get it? That's all it is. So I wasn't really lying to you guys where I said I could just show you the original one and then just say, you guys figure out how to make E+, right? If you know how to make the E+, then everything else from there kind of just falls out the same. Got it? There is no difference. Good? It's not too bad, right? Guess what we're going to learn next time? More of the same, right? So it's not going to be any different next time. But we are going to learn some other important reactions. We're going to start to add different functional groups. And that's kind of going to be I don't want to say the point or the utility of aromatic rings. They're very, 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 very reactive. You're like, that's not what you told us before. What I mean is there's a lot of different reactions we can do to add functional groups to them. They're also pretty easy to control because they're not very reactive. Do you guys catch what I mean with this? Because we have to set up special conditions, we have to generate strong electrophiles. They're not going to necessarily behave in the same way as some of the other functional groups that are present in molecules, right? So we use both of the traits that we've kind of learned, right? They're unreactive in certain conditions, but reactive under others, and we can do a lot of different reactions under those specific conditions. That's what I mean by they're highly reactive, okay? And we can add different functional groups, nitros, sulfurs, halogens, right? We're going to learn how to add carbon bonds, right? We're going to add ketones to it, we're gonna add amines to it, we're gonna add fluorines and cyanos and everything under the sun, okay? Everything under the sun. Good? All right, so I'll see you guys tomorrow. We'll have the first lab exam and then, no, I'm just kidding. Right, so we're just gonna be finishing up the raspberry lab there, and then we'll adjust the schedule as we need to, okay?